This is the Lecture 1 of Gallium Nitride Field Effect Transistor, Gate Driver IC Design. Introduction: Gallium Nitride Transistors for Future Power Management Systems. The power management landscape is shifting faster than ever, and gallium nitride technology is driving that transformation. In this lecture, we'll begin by examining current trends in power management integrated circuit design and why traditional silicon solutions are struggling to meet the demands of electric vehicles, renewable energy, and high-density electronics. Next, we'll compare gallium nitride field effect transistor parameters with their silicon and silicon carbide counterparts to highlight exactly where gallium delivers a performance edge. Finally, building on that, we'll explore the merits of using gallium nitride transistors, including their exceptional switching speed and the significant size and efficiency improvements they bring to power stages. By the end of this lecture, we'll be able to reveal the device behavior that makes this technology so enabling for future power management systems. The trend of power management systems. In the recent years, growth areas such as electric vehicles and renewable energy systems are increasing the demand for more sophisticated power management solutions. These applications push power electronics to operate in tougher conditions, delivering more power in less space, switching faster to boost performance, and reducing energy loss to meet strict efficiency goals. Traditional ease-of-use designs, which focus on simplicity over performance, can no longer meet these stricter requirements. As a result, the industry is moving toward more compact and fully integrated power electronic solutions. By reducing the number and size of external passive components, these integrated designs improve performance, shrink system size, and support the next generation of advanced power architectures. Gallium nitride transistors provide key advantages that directly address the unique challenges faced in power electronics design for these rapidly growing application areas. Gallium nitride versus silicon carbide. Field effect transistors. Before going on to the details of comparing the critical parameters of the types of transistors mentioned, let's first briefly discuss the basic operation of gallium nitride transistors. Gallium nitride transistors operate similarly to silicon transistors, where a positive bias on the gate relative to the source creates an electric field that attracts electrons to form a bidirectional conduction channel between the drain and source. This provides a very low-resistance path for current flow. When the gate bias is removed, the electrons beneath the gate disperse back into the gallium nitride material, re-establishing the depletion region and restoring the device's ability to block voltage. Let us now examine in detail the critical performance parameters in which gallium nitride devices offer clear advantages over silicon transistors. We begin our comparison of gallium nitride and the conventional silicon transistors with gate capacitance, a parameter that strongly influences switching behavior. In CMOS silicon power devices, illustrated in the upper right corner of the slide, the total gate capacitance, commonly referred to as CISS, typically falls in the 2 nanofarads to 6 nanofarads range. Such capacitance levels slow the charging and discharging of the gate, limiting switching speed and increase in energy loss. Gallium nitride devices, shown in the lower right corner, operate on the same basic gating principle, but their lateral structure and wide band gap properties naturally yield much lower CISS values, typically 0.2 nanofarads to 1.5 nanofarads for similar voltage and current ratings. This substantial reduction in gate capacitance allows gallium nitride transistors to switch significantly faster, cutting switching losses and enabling higher overall power conversion efficiency. Next parameter is the gate charge requirement, QG. Gate charge is directly tied to the previous parameter, gate capacitance. It represents the amount of charge the gate capacitance must receive to reach the required gate voltage and fully turn the device on. Silicon devices typically need 50 to 150 nanocoulombs, whereas gallium nitride requires only 5 to 30 nanocoulombs, enabling much faster and lower loss switching. Gallium nitride transistors operate with a significantly lower gate drive voltage, typically 5 to 6 volts, compared with the 10 to 12 volts required by silicon transistor. This smaller change in gate voltage is enough to fully enhance the device, meaning the transistor is completely turned on. As a result, gate driver losses are reduced and level shifting requirements are eased, especially in high-frequency, high-density power conversion designs. Next is the delta VDS over delta T, the drain-to-source voltage switching speed. Silicon transistors typically switch at 10 to 20 volts per nanosecond, while gallium nitride devices reach 50 to 150 volts per nanosecond. This parameter reflects how quickly the drain voltage can change during switching. Faster voltage transitions mean shorter switching intervals, which directly reduce switching losses and heat generation, allowing more efficient and responsive power conversion operation. Next parameter is the switching frequency, which is related to parameters previously discussed. Gallium nitride transistors achieve much higher switching frequencies than silicon MOSFETs, primarily because their far higher delta VDS over delta T allows the drain source voltage to transition much faster. Their gate structure also requires only 5 to 6 volts to fully turn on, compared with silicon's 10 to 12 volts, and the gate charge is significantly lower. This means the driver can move charge in and out of the gate far more quickly, letting the device switch states with minimal delay. Assuming the same duty cycle, gallium nitride's rapid voltage transitions and fast gate charging leave more usable time in each cycle, allowing the circuit to operate at much higher repetition rates. As a result, silicon is typically limited to 50 to 200 kHz, while gallium nitride reaches 500 kHz to several megahertz. Next is voltage rating, or the maximum drain to source voltage. Gallium nitride devices are typically rated from 100 to 650 volts, while silicon transistors span roughly 20 to 900 volts. This voltage rating defines the maximum drain-to-source voltage the device can safely block when off. Although silicon covers a broader range, gallium nitride transistor delivers far lower losses and faster switching in the 100 to 650 volt class, making it the superior choice for high-efficiency power applications. The last one is the current carrying capability, ID max. Silicon transistors typically handle 10 to 25 amperes, while gallium nitride devices of similar size often support 20 to 40 amperes. This current carrying capacity indicates how much continuous drain current the device can deliver without exceeding thermal or reliability limits. Gallium nitride transistors' higher capability allows more power to be delivered from a smaller footprint, improving power density, reducing heat, and enabling more compact, efficient converter designs. Here's the summary table comparing gallium nitride, silicon, and silicon carbide transistors' key parameters. Merits of using gallium nitride field effect transistor. Let us now examine why gallium nitride transistors enable power electronics designers to meet the unique demands of electric vehicles and renewable energy systems, particularly the increasing need for highly miniaturized power solutions. In a DC-DC buck converter, for example, whose simplified schematic is shown on the right, the inductor, Lx, values decrease as switching frequency increases, as illustrated in the equation. Similarly, output capacitor, Cout, sizing for ripple and transient response also scales inversely with frequency. Because gallium nitride transistors can operate at much higher switching frequencies than silicon, designers can significantly shrink inductors and capacitors, achieving more compact and efficient power stage implementations. When power management systems employ gallium nitride devices as power transistors, the required passive components are much smaller in physical size and will also exhibit lower losses. As a result, the overall power solution becomes significantly more compact. Inductors, capacitors, and heat-spreading areas can all be reduced, enabling higher power density in the same footprint, or the same performance in a far smaller one. This supports ultra-miniaturized power architectures. Shown on the right is a power converter electronic circuit that uses silicon and gallium nitride as power transistors. You can see that the power solution using gallium nitride has a much smaller and more compact physical size than the one using silicon. Gallium nitride transistors' low gate charge, reduced capacitances, and inherently fast switching enable the entire gate driver function to be implemented directly on chip, something far more challenging to achieve with silicon-based devices. Because gallium nitride device requires much lower drive energy and relies on fewer and smaller support components, elements traditionally placed off-chip, such as the bootstrap capacitor, C-boot, can now be integrated within the driver itself. This significantly simplifies the external bill of materials, minimizes parasitics, and supports the creation of compact, robust single-package power stages. Most importantly, this capability sets the foundation for the central theme of this entire lecture series: the design and development of a fully integrated gallium nitride gate driver.
End of the lecture.